All right, so hi everybody, welcome back. What we're going to be doing today is a continuation of our Chapter 15 lecture on mechanical waves. And where we left off last time was we derived a general formula for the displacement as a function of position and time for a sinusoidal wave moving in one dimension. Okay, so this d of x and t function. So what we're going to do in this example is come up with a specific function where we actually plug in the values of all the constants for this wave. So the graph that you see here shows a snapshot of a wave traveling in the positive x direction at 200 meters per second. So a few questions about this. What is the amplitude of this wave, A? What is the wavelength, lambda, of the wave? What is the frequency, f, of the wave? And then write out the function d of x and t for this wave. So pause the video for a second, see if you can work this out based on the formulas we derived last time, and then we'll go through it together. Okay, so right away there's some information we can get straight from the graph. And that would be the amplitude A, which again is the maximum displacement of the wave from equilibrium. And just by inspecting the graph, we can see that the amplitude is 1 centimeter. Also, we can determine the wavelength straight off the graph. Remember, this is the distance between two peaks of our wave. That's lambda right there. And again, straight from the graph, we can determine that this distance is 2 meters. Okay, we also know the speed of the wave, v, is 200 meters per second. Okay, also, since the wave is moving in the positive x direction, when it comes time to write out the function for the wave, we're going to use minus omega t. So to remind you, the general form of d of x and t for a sine wave moving in one dimension is the amplitude A times sine kx minus or plus omega t plus phi. So what we need to do is pick the negative sign because we have a wave moving in the positive x direction. Okay. So with that said, let's do some calculations. The first thing we can calculate is the frequency, because remember, v is equal to lambda f. That's the fundamental relationship between the speed, wavelength, and frequency of a wave. So since we know v and lambda, we can solve for f, which is equal to v over lambda. And therefore, we have 200 meters per second divided by 2 meters, which is exactly 100. And we're left with inverse seconds as our unit, which is equivalent to hertz. So we can say this is 100 hertz. Okay, now if we want to write out the specific function for our wave here, d of x and t, we're going to need to calculate k, that's called the wave number, and omega, that's the angular frequency, and also phi, the phase angle. So let's start with k. K is equal to 2 pi divided by lambda, by definition. So the way you can think of this is we have 2 pi, implicitly the unit here is radians, and we're dividing by lambda, which is 2 meters, so that just works out to pi. Units are radians per meter. Okay, you'll also recall from last time that we have omega equal to 2 pi times f. And again, implicitly, this 2 pi carries a unit of radians along with it. And then we multiply by f, which is in inverse seconds, 100 inverse seconds. So what we have is 200 times pi radians per second. Okay, so we're almost done. The only thing that we really have left to do is to calculate the phase angle phi. And to do that, we can note that the displacement of the wave when x is equal to 0 and t is equal to 0 is equal to a times sine, and then we're going to have k times 0, because we're plugging that in for x, plus omega, or I should say technically minus omega times 0, plus phi. But the point is, the only thing left in the sine function is phi. The rest is just 0. So we have a times sine phi. Okay, now from the graph, we can just look and see what is the displacement when x is equal to 0 and t is equal to 0. So remember, this is a snapshot of what the wave looks like at t is equal to 0. So we already have that part covered. Now we just need to look at x equals 0, which is right here. And it looks like the displacement of the wave is minus the amplitude. So minus a is how we could write this. So I have a sine phi is equal to minus a. So sine phi is equal to minus 1. And what angle solves this for us? Well, phi is equal to, we could write this in two ways, minus pi over 2 or 3 pi over 2. Let me actually go into a little bit more detail on that. I'm going to remind you of the unit circle. Sine of an angle is equal to the y-coordinate on the unit circle. So remember, we have x and y like this. We have the unit circle with the center at the origin. So if sine of an angle is equal to the y-coordinate on the unit circle, we're interested in where the y-coordinate is minus 1, and that happens right down here. So we can write the angle as 3 pi over 2 if we're going like this, counterclockwise. Or if we're going the other way, we could write it as just minus pi over 2. That's actually the same exact angle, it's just a different way to get there. So either way to write it is fine. And of course, implicitly the units here are radians. So how do we write the solution for this wave, d of x and t? Well, we have the amplitude, which is 1 centimeter, multiplying sine of k times x. Remember, k was pi radians per meter times x. And then we have minus omega, which is 200 pi radians per second times t. And then we have minus pi over 2 radians. So that right there is the general solution for this wave. It describes exactly what's going on with the wave. You can plug in any value of x and t, and this will tell you exactly what the displacement of the wave is for that value of x and t. So that's how this works. Okay, so let's do another one of these. The graph on the left here shows a snapshot of a wave traveling in the minus x direction. So this is at t is equal to 0. We're looking at the displacement as a function of x, as a function of position. That's what's on that graph. The graph on the right is a history of the displacement of the wave at position x equals 0. So instead of looking at a snapshot in time, now we're looking at a fixed position in space, so x is equal to 0. And we're looking at how the displacement changes over time. So displacement versus time is what you see on this graph. So the first question is, what is the speed of the wave depicted in these two graphs? And then second, let's write out the function d of x and t for this wave. So again, pause the video, see if you can work this out, and then we'll go through it together. Okay, so we'll start by thinking about what information can we get straight from the graphs just by looking at these two graphs. So if we look at the graph on the left, we can see a few things. First, the amplitude. Okay, that's the height of the wave from the equilibrium position all the way to the crest. The amplitude is 1 centimeter. That's the maximum displacement. We can also take a look at the wavelength. So on the first graph, again, since the horizontal axis is x for position, lambda tells us how much of a distance we have between one peak and the next of this wave. And for lambda, we have 0.6 meters. Okay, what about from the second graph on the right? Well, we could also use that to determine the amplitude is 1 centimeter, same as before. But we can determine the period from this one because time is now on the horizontal axis. The amount of time it takes to go from one crest of the wave to the next is the period t. And we can just read that straight off the graph. That is 0.2 seconds. Okay, now for some calculations. First thing we'll note is that the frequency of the wave is 1 over the period, so 1 over t. We have 1 over 0.2 seconds. That comes out to 5 seconds inverse, or we could say 5 hertz. That's the frequency. Now the angular frequency, omega, is 2 pi times f. So we're going to have 2 pi, implicitly we're talking radians here. Frequency is 5 inverse seconds. So that's 10 pi radians per second. Okay, what about the wave number k? K is 2 pi divided by lambda. So we have 2 pi radians implicitly divided by lambda, which is 0.6 meters. 2 over 0.6, if we write that as a fraction, is 10/3. And then we have the pi factor out front. So we have 10/3 radians per meter. That's k. And we would like to know the speed of this wave. How fast is it propagating? For that, we'll use the relationship v is equal to lambda times f, where lambda is the wavelength equal to 0.6 meters, and f is the frequency equal to 5 hertz or 5 inverse seconds. This comes out to a nice round number, 3 meters per second. So that's our propagation speed. And at this point, I'm just going to write on the side the general solution for this wave. For d of x and t is a times sine kx minus or plus omega t plus phi. Now this particular wave happens to move in the minus x direction. So the wave moves in the minus x direction, which tells us that when we think about the general formula, we should be using plus omega t. Yeah, plus omega t. All right, so the last thing to work out then is the phase angle phi, because we have the amplitude, we have k, we have omega, we need to know phi. And then we'll have everything we need to write down the solution for d as a function of x and t for this wave. So here's what we have. If I plug in 0 for x, 0 for t, what we're going to get is a times sine k times 0 plus omega times 0 plus phi, which means we'll just have a times sine of phi, because this goes to 0. And okay, well, let's take a look. When x is equal to 0, let's look at the graph on the right here, and t is also equal to 0, this is our displacement. In other words, we're at the peak or the crest of the wave. The displacement is equal to a, the amplitude. And so sine of the angle is equal to 1. The angle in question is pi over 2. So if you ask the question, sine of what angle gives you 1, the answer is pi over 2 radians. Okay, so now we just write down the final answer. D of x and t is equal to 1 centimeter times sine of k, which is 10 over 3 times pi radians per meter. That multiplies x. Then we have plus omega, which is 10 pi radians per second. That multiplies t. And then we have plus phi, which is pi over 2 radians. That's the solution we're looking for this wave. Okay, so the next thing I want to show you are some animations of the two waves that we solved for in the previous examples. So in the first example, we found that d as a function of x and t is equal to 1 centimeter times sine pi x minus 200 pi t minus pi over 2. And in the second example that we just did, we found that d of x and t is 1 centimeter times sine 10 pi over 3x plus 10 pi t plus pi over 2. So that's what we have. And what I'm going to show you are animations of those two waves. We're going to have displacement of the wave on this axis here, measured in centimeters. And then we're going to have x in meters on this axis. So displacement versus position. So right now you're just seeing a still image, but when I play the animation, you'll see the wave in the first example moving to the right. And this one is moving much faster than the other wave. This moves to the right, remember, at 200 meters per second, so you're seeing it go by very quickly. The second example, we have a wave moving to the left at just 3 meters per second, so it's moving much slower. But again, you can see that one is moving to the left, the other is moving to the right. Another difference between the two is the wavelength. In the first example, the peaks of the wave are further apart, so it has a longer wavelength. In the second example, we have a shorter wavelength. So that's a comparison of these two examples. Okay. The next thing we want to take a look at is how do we calculate the speed of a wave on a string? So the general thing that we're looking at here is a string that has a mass per unit length given by what we'll call mu. And it's kept under a constant tension, which we'll call Ft. The end of the string is pulled upward. Okay, so next, let's talk about the speed of waves on a string. So what we're going to do here is derive a formula for the speed of a wave that travels down a string. And the reason we're doing this is a situation that comes up quite a bit. We're going to need a formula that we can use to calculate how fast a wave is moving along a string. So here is the setup for the derivation. We have a string that has a mass per unit length, which we'll call mu. So mu is the linear mass density of the string. That's what we call it. This is the mass divided by the length, okay? Mass per unit length. The string is also kept under some amount of tension, which we'll call Ft. That's the tension in the string. And we'll assume the tension is constant. It's not changing over time. It's the same tension everywhere in the string. Okay. So how can we create a wave that travels down the string? Well, one way we could do it is to take the end of the string and just pull up on it at some speed. So in other words, we're going to take the end of the string and move it upwards at a speed which we'll call v prime. So that's how fast the end of the string is moving up. So as a result of doing this, we're going to create a little kink in the string like this, and we'll create a wave that's moving to the right down the length of the string. So the edge of the waveform here is moving to the right at a different speed, which we'll call v. So v prime is just how fast we're pulling up on the end of the string, but v is what we actually want. This is the speed of the wave that we're creating on the string, okay? So as we do this derivation, we're going to make an assumption that the displacements are small. What that means is if we look at this angle here, theta, that we create by pulling up on the string, we're going to assume that that's a very small angle. In other words, theta is a lot less than 1 radian. That's what we'll assume throughout this derivation. Okay, so the first thing we'll do here is draw the vector Ft for the force of tension, and we can break it down into components. Now, the horizontal component would be Ftx, and the vertical component would be Fty. Now, since tension acts along the length of the string, this angle theta is the same one that we have in the original diagram. And of course, we have a right angle between x and y. Another thing we can do is note that there's a certain length here of the string that's been pulled up. So we'll call L the length of the string segment. And we can use that to construct another triangle, because if L is the length of the string here, we can sort of break this, like before, into a vertical and a horizontal component, and note that the angle theta is still there, and the right angle between vertical and horizontal is still there as well. So what do we make of this horizontal piece? Well, that would just be the distance that the wave has moved. And if the wave is moving at speed v, if we multiply that by a time, which we'll call delta t, that will give us the distance. What do we make of this vertical piece? That would be the distance the string moves up. So again, we can think of this as a speed times the time. In this case, the speed would be v prime, and then multiply by delta t. So I didn't draw the triangles very well, but they're similar triangles. Okay? They have the same proportions because they have the same angles. And because of that, we can come up with relationships between them. For example, if we take tangent of the angle theta, that's the opposite side over the adjacent. Using the first triangle, we have Fty over Ftx. That's how we would think of the tangent there. But in the second triangle, we have v prime delta t over v delta t. And those are the same thing because we're talking about the same angle here. So I can use this then to solve for Fty. What's Fty? That's equal to Ftx. Cancel out delta t's times v prime over v. Okay, now what's Ftx? That's going to be the magnitude of the tension force times cosine of the angle. That's how we think of this side Ftx. So that'll multiply v prime over v, just like before. But what we're assuming here is that the angles are small. In other words, we're making what's called the small angle approximation, where theta is a lot less than 1. There are two things we can get from this. First, sine theta is approximately equal to theta when you're dealing with a very small angle. Also, cosine theta is approximately equal to 1 when you're dealing with a very small angle. So therefore, from what we have above, we can say Fty is approximately equal to the magnitude of the tension force. Cosine of theta is about 1, so that's just v prime over v. So that's our first result. Let's call this result A. Okay? The next thing we can do is think about how we can apply Newton's second law to the upward moving string segment. Okay, So Newton's second law is F equals ma. Let's focus on the y direction here for now. So the net force in the y direction is m times ay. That's one way to write it. But you could also think of it this way. Delta p over delta t. So m times a is the same as delta p over delta t. Those are two different ways of writing Newton's second law. So we'll think about it the second way in this case. Now let's think about what delta p is equal to. This is the change in momentum of the rope segment. Okay, so after we're pulling it up, it has a momentum of m times v prime, because it's moving upwards at a speed v prime. But before we started pulling on it, it didn't have any momentum at all, so the change is m times v prime. Okay. The next thing we'll think about is the linear mass density, which we call mu. That would be the mass of the string divided by the length. Okay, so in other words, if we want to know what the mass is of that little string segment, we would take mu, that's the mass per unit length, and then multiply by L, which is the length. Okay? Okay, to take this a little bit further, let's actually go back to the second triangle here. Okay, this one. And let's think about how we can write down cosine of the angle theta that appears in that triangle. Remember, cosine is the adjacent side divided by the hypotenuse. The adjacent side is v times delta t, and the hypotenuse is L. And remember, we're assuming small angles, so cosine theta is approximately equal to 1. So in other words, L is approximately just v times delta t, which if we use that in our previous expression, m is equal to mu times L, so it's mu times v times delta t. And then finally, what we can say is the change in momentum, delta py, is that mass, which, here, let's just plug it in, is mu times v times delta t times v prime. Okay? So that's coming right from here, plugging in our result for the mass. Okay, so now let's use Newton's second law, where the net force in the y direction is equal to delta p over delta t. The only force we need to think about in the y direction is Fty. And using all the approximations we made, that's about equal to delta p, which is mu times v prime times delta t, divided by delta t. So that delta t is canceling once again. And we're left with Fty is approximately equal to mu times v prime. Again, we're assuming small angles here. And this, let's call it result B. Okay, so here, let me put a box around result A. For Fty, this is what we got. And then result B, we have a different expression for Fty. Of course, we can just set them equal to each other. In other words, A is equal to B. They're both expressions for Fty. And here's what that gives us. So we have the force of tension, the magnitude of that force, times v prime divided by v. That's result A. Equals mu times v prime. That's result B. So first, we'll cancel out v prime. That doesn't even come into play here. And what we're trying to do is solve for v, the speed of the wave. So if I multiply on both sides by v and divide on both sides by mu, I'm going to have Ft over mu is equal to v squared. And so therefore, v, which is the speed of our wave, is equal to the square root of ft divided by mu. So in other words, the speed of a wave on a string, it only depends on two factors: the amount of tension in that string and the mass per unit length, that's what we call mu, of the string. And so there's the result, that the speed of a wave on a string is given by v equals the square root of ft divided by mu. Okay? So with that said, let's do a practice question. We have a uniform cord which has a total mass of 12.5 kilograms and a total length of 135 meters. It's tied to a post at both ends, here and here. You pluck the cord at a distance of 25.5 meters away from post A. So this is where you pluck the cord. As a result of doing that, you send a wave down the string, and it takes 2.45 seconds to reach post B. So you pluck it here, the wave goes down the string, and it takes 2.45 seconds to get here to post B. So what is the tension in the cord? Try to work this out using the result we just derived. Pause the video, see if you can work it out, and then we'll go through it together. Okay, so we'll start by remembering the definition of speed. So the speed at which the wave moves is equal to the distance that it covers divided by the time. And this is the distance in question. It will be the distance from where you are to post B. And of course, that distance will be the full length of the rope, which is 135 meters minus 25.5 meters. And then the time it takes to cover that distance, again, is 2.45 seconds. Okay, if you crunch these numbers, you're going to find it comes out to 44.69 meters per second, and we'll keep 3 sig figs on that. Next, let's think about the idea of linear mass density, which of course is the mass divided by the length of the rope. In other words, we have mu is equal to 12.5 kilograms, that's the total mass, divided by the length, 135 meters. So this works out to 0.09259 kilograms per meter. We'll keep 3 sig figs on that. And then, by the way, up here, speed is v. Okay. Now remember, what we just derived is that the speed of a wave on a string is the square root of the force of tension divided by the linear mass density. What we want is the force of tension. So we'll start by squaring both sides. V squared is Ft divided by mu. So therefore Ft is mu times V squared. Okay, so mu is equal to 0.09259 kilograms per meter. And then V is 44.69 meters per second, and we're squaring that. Now, let's think about how the units work out. We have kilograms. We have meters squared on top, but we're dividing by meters, so overall just one factor of meters on top. And then second squared on the bottom. By the way, this is a Newton. And if you crunch the numbers, you're going to find it comes out to 184.9. Keeping 3 sig figs, we get 185 newtons. So that's how much tension must be in the string in order to create this sort of wave. Okay, so next, let's talk about velocity and acceleration as it relates to this result that we derived. Remember, d of x and t gives us the displacement of particles in a 1D medium that carries a sine wave. And again, it's a function of both position x and time t. And the general form that we have is d of x and t is equal to a sine kx minus or plus omega t plus phi. That is the general form that we have. Now, one thing we could do is take the derivative of this to find the velocity of particles in the medium. So in other words, the velocity as a function of x and t would just be the derivative of this displacement with respect to time, but we have to be a bit careful about how we do this. We only are interested in finding the derivative with respect to time, and we want to keep all other variables like x constant as we take that derivative. So this is what we call a partial derivative. It means take the derivative with respect to time only and treat everything else as a constant. So this kind of squares with what we know about velocity. It's the first derivative of position with respect to time. But keep in mind that this is not the same as the velocity that the wave itself is moving with. Remember, particles in the medium that are carrying a sine wave are going to be oscillating up and down like this around some equilibrium position. The wave is moving at some speed which is completely independent of that. Okay, so we're talking about the velocity of the particles in the medium, not the velocity of the wave itself. So in a similar way, we can calculate the acceleration of particles in the medium. That would just be done by taking another derivative. In other words, a acceleration as a function of x and t would be the second derivative with respect to time of that displacement. Okay, and again, this is another partial derivative. So let's get a little bit of practice using these ideas. Let's say we have a transverse wave on a string, which is described by this function. D of x and t is equal to 0.125 times sine of 0.354 times x minus 1.45 times t. I'm leaving the units off of this, but everything is in SI units. Okay, so the question is, what is the maximum vertical speed of any point on the string? So remember, as a wave moves by going to the right, let's say, any given point on the string is going to be vibrating up and down like this. So what is the maximum speed of that vibration? And as a follow-up, what is the maximum vertical acceleration of any point on the string? So again, as a point on the string vibrates up and down like this, what is the largest acceleration that it will have? So pause the video, try to work this out. Again, you'll take the first derivative with respect to time to get velocity. You'll take the second derivative to find acceleration. So do that, see if you can work it out, and then come back to the video to see what the answer is. Okay, so we'll start with our function d of x and t is equal to 0.125 times sine of 0.345, that's what I meant to say, times x, and then minus 1.45 times t. There it is. Okay, so the velocity as a function of x and t would just be the first derivative with respect to time of that displacement. So let's work that out. The first derivative with respect to time, well, we have a constant out front of 1.25, and the derivative of sine is cosine. So we'll have cosine of that same exact function before. But we also need to take the derivative of what's inside with respect to time. So remember, x, that's just a constant for our purposes. So we only need to think about the derivative of the second term, which will bring out minus 1.45. Okay? And of course, if we look at cosine, that's just a function that ranges between -1 and 1. So therefore, whatever is out front here is the maximum velocity that we're looking for. This is Vmax. And if you calculate what Vmax is, 0.125 times 1.45, you're going to get 0.18125 meters per second, keeping 3 sig figs, 0.181 meters per second. So, in other words, as the string moves up and down, the highest speed that it will attain is this, 0.181 meters per second. Okay, so next, we'll do acceleration as a function of x and t. That's going to be the second derivative with respect to time of our displacement. So that'll be second derivative. And of course, we already have the first derivative. So what we can do is take another one. So we have 0.125 and minus 1.45 out front, just like before. But when we take the derivative of cosine, we get negative sign. So here's what I'm going to do. I'm going to put a negative out here, and then cosine changes to sine. And we have 0.345x and minus 1.45t inside of here. And again, we have to take the derivative of what's inside of the sine function, which just brings out another factor of minus 1.45. So here's how I'm going to do that. Minus 1.45 is now being squared, okay? And just like before, sine is a function that ranges between minus 1 and 1. So whatever this factor out front is, that must be our maximum acceleration. So 0.125 times 1.45 squared. What does that work out to? 0.2628 meters per second squared. Round that up to 0.263 meters per second squared. That is our maximum acceleration, again, as the string vibrates up and down. Okay, so the next topic here is energy transported by waves. Let's get into this. So I want you to remember that when you have a mechanical wave that propagates through some kind of medium, so you have a wave moving through some material, it doesn't carry matter over large distances because the particles that make up the medium are just oscillating around some equilibrium position. They're not moving long distances when a wave comes through. So let's take a look at this animation of a pulse being created on a rope. So the hand that holds the end of the rope just moves up and down, and it creates a little pulse that moves to the right. So it's not the case that particles of the rope that start off over here end up over here, right? Those don't move large distances. All that's happening when the wave comes through is particles simply move up and down around their equilibrium positions. So what's moving to the right along with that waveform is not actual matter, it's energy. So as that waveform moves through, it's energy that's being carried by the wave, but not actual matter or particles. So related to this idea that a wave carries energy is the intensity of a wave. So this is the definition of intensity. Intensity is given by capital I, and intensity is the energy per unit time passing through a surface that's perpendicular to the direction of the wave propagation divided by the area of that surface. So that's kind of a lot. Let's draw a picture so we can see what this really means. Okay, so you have some kind of wave that's moving to the right in this picture. And so what we do is we construct a little surface, S, that's oriented perpendicular to the way the wave is moving. Okay, so this is our surface S. So we have the wave actually going through the surface that we label S. Okay, so of course, as the wave moves through, there's some energy moving through that surface. If we divide by the time, as well as the area of that surface on the bottom, that gives us the intensity of the wave. So again, it's the energy per unit time per area moving through this surface, which is oriented perpendicular to the wave propagation. Okay, that's how we think about intensity. Now, to give you some more concrete examples, let's think about the intensity of a light wave. So when we talk about the intensity of the light wave, that's what we perceive as brightness. So when a light looks really, really bright, it has a very high intensity. When we talk about the intensity of a sound wave, that's what we perceive as loudness. So a very low intensity sound wave is very hard to hear. Very high intensity sound wave sounds very loud, okay? Now, when we think about the units for intensity, well, first of all, we have energy divided by time. So our energy unit would be a joule, and our time unit would be a second, but a joule over a second is a watt. When we look at area, we would use a square meter to measure area in the SI system. So the SI unit of intensity is a watt per square meter. Watts over square meters is our SI unit of intensity. So the next thing we're going to do is derive an equation for the intensity of a mechanical wave that's shown here. So before we describe the equation, let's do the derivation to see where this comes from. Okay, so to start, let's just copy down the definition of intensity. Intensity is energy per unit time per area passing through our surface. So symbolically, intensity is given by capital I, energy given by E, time is T, and then for the area, I'm going to call this S. So think of this as the area of our surface, okay? Now, when a wave passes through, it causes the particles in our medium to oscillate. So particles in the medium will oscillate. And we also have a way of describing the energy of those oscillations, 1/2 Ka squared from the last lecture. Also, omega, which is the frequency of those oscillations, is root K over M. So this is what we took a look at when we were reviewing simple harmonic motion. So the reason I'm bringing this into play is because if we rearrange this equation by squaring both sides and then multiplying through by m, we can get K is equal to m times omega squared, which means we can write the energy of the oscillating particles as 1/2 times m omega squared times a squared, where, by the way, a is the amplitude. So that's why up here I used the variable s for the area, not to confuse it with a, the amplitude in this equation. Okay, another substitution we can make is this. Omega is just 2 pi times f. So therefore, the energy can be written as 1/2 times the mass times 2 pi f squared times a squared. And then if we just sort of simplify this, we're going to have an overall factor of 2 out front, pi squared, m squared, just m, then f squared, and then a squared, okay? So this describes the energy of the oscillating particles in our medium. So we can take this even further by introducing the concept of density. Remember, density is mass per unit volume. So the way I'm going to write this symbolically is rho for density is m over v, mass over volume. So the mass is the density times the volume. Okay. But what is the volume we're actually talking about here? Remember, we're imagining a wave that passes through some kind of surface. And we can draw the surface as this sort of box, this little box-shaped thing, like this, where S is the area of the surface that the wave is passing through, but there's also a thickness here. So how can we think about the thickness? Well, let's think of this as the distance the wave moves. And of course, that distance can be written as the speed of the wave times the time. Okay, so in other words, I'm going to write this as Vt. So this is getting a little tricky. There's a lot of variables floating around here, but I'm using little v for the speed. That's what you see here. And then uppercase V for the volume. Okay, so what is the volume of this slab of material that I just drew? Well, the volume would be the area of the slab times the thickness. In other words, capital V for volume is equal to the area S times the thickness, which is little v times t. Okay, so therefore, remember the mass is the density times the volume. So the mass would be the density times S times little v times t, subbing that in. And then finally, remember our expression for energy has the mass term in there. So let's sub in for mass what we just figured out over here. Energy is equal to 2 pi squared. Now the mass is going to be rho times S times V times T. And then we'll have F squared times A squared. Okay, so remember, at the very beginning, the whole point of this is to come up with some expression for intensity. The intensity of the wave is the energy that passes through this surface divided by time divided by the area. So basically, we have this formula for the energy. To get the intensity, we're going to take that expression for the energy and again divide by time and area. So here I have 2 pi squared rho S V T F squared A squared, but basically I'm just dividing out the S and the T, so those cancel to get the intensity. So therefore the intensity is just 2 pi squared times rho times V times F squared times A squared. That's the expression for the intensity of a wave that we wanted to derive. Okay, so that's where this expression for the intensity of a wave comes from. Again, it's 2 times pi squared times V times rho times F squared times A squared. A lot of variables floating around there. Of course, I is the intensity. V is the speed of our wave. Rho is the density of the medium that our wave is moving through. So if it's moving through air, you would use the density of air, for instance. F is the frequency of the wave. And then A is the amplitude of the wave. So one really important thing to take note of here is that the intensity of the wave goes like the amplitude squared. So the intensity depends on the amplitude squared. That's going to come up later on. Okay, so we've seen how to deal with waves that move in one dimension. We've done a few problems dealing with waves that move on a string or they move on a rope of some kind. Those are one-dimensional mediums. What we want to do now is deal with waves in 2 or 3 dimensions. And part of what makes this a little tricky is just knowing how to visualize what's going on. So I'm going to tell you about 2 useful tools, things called wavefronts and rays. So we can kind of sketch out what's going on when we have a wave that moves in 2 or 3 dimensions. Okay, so let's start with wavefronts. A wavefront is a collection of points on a wave that are in phase. That means they're oscillating together. They're oscillating in unison. So on a diagram, when we draw a wavefront, it usually represents the peak of a wave. So in other words, if I draw a wavefront, all of the points on that wavefront are all hitting the peak of the wave at the same time. Okay? Now, a ray is just an arrow that indicates which way the wave is moving. It indicates the direction of your wave's propagation. Now, one thing that we'll see when we go into the 2 examples here is that the rays are always perpendicular to your wave fronts. Okay, so let's start over here with the 2-dimensional case. Okay, So we're going to imagine waves that are emitted from a single point, okay? So to give you something a little bit more concrete to think about, what's an example of a two-dimensional medium that can carry a wave? Well, classic example is just the surface of water. Imagine you have a pond, okay? And there's a little mass inside of the pond that's just bobbing up and down, okay? And we know intuitively, right, if you take a little mass and you bob it up and down at some point in a pond, it's going to create ripples in the water that move outwards, okay? So what's being shown here with these red arrows are the rays. Again, the rays indicate the direction of your wave propagation. The waves should be moving out in all directions away from that source. So that's what's happening here. On the other hand, your wave fronts are these white lines, these white circles. And again, what those represent is a bunch of points on your wave, points in the pond, in this case, that are all hitting the peak at the same time. So in other words, let's take this wavefront. This is just a collection of points that are all peaking at the same time. Also over here, this wavefront, that just is a bunch of points that are all peaking. You're hitting the crest of the wave all at the same time, and then you can just keep going out. That's what the wavefronts represent, okay? So if we actually look at this animation then, okay, as our little mass bobs up and down in the pond, we know it sends out these ripples, and we can visualize those as these circular wavefronts that are moving outwards away from the source. And the rays are just there to tell us which way those wavefronts are moving. Okay? So the point here is when you have a two-dimensional medium and you have some waves emitted from a point in that two-dimensional medium, the wave fronts that are emitted are going to be little circles that just move outwards. Now, let's say we have the three-dimensional case over here. So in that case, your wave fronts are going to be spherical. So here we have a point that's emitting waves. So that's the source of the waves right here. And it's emitting these wave fronts that move outwards in all directions, just like in the two-dimensional case. But instead of being circular, the wave fronts are now spherical. Okay? So that's how we can visualize waves that move in 3 dimensions. And what would be an example of this? Well, let's say that little source of the waves is some kind of person yelling, right? So if you just kind of stand in the middle of the room and yell, you're going to send out sound waves in all directions. That would be represented by these spherical wavefronts moving outwards. That's just an example of, waves that could move in 3 dimensions, sound waves in air. Okay, and that brings us to the inverse square law. Okay, so we need to first define a term called isotropic. Okay, so an isotropic source of waves will radiate energy evenly in all directions. So in other words, if your source of the waves is isotropic, it just spreads out its waves evenly in all directions. Okay, and so that takes us to the inverse square law. Now, before we get into this, there's a term that I need to define for you, which is something called isotropic. So an isotropic source of waves is something that radiates energy evenly in all directions. In other words, it doesn't have any sort of preferred direction where it's radiating more energy. It just radiates the energy evenly in all directions. So to give you an example, something like the sun or a light bulb would be a good example of an isotropic source of light waves. Because again, if you take a light bulb and you're standing next to it, let's say, and you sort of shift your position, maybe you stand on the other side of the light bulb, it looks just as bright because again, it's radiating that light energy evenly in all directions. On the other hand, if you had something like a laser beam, okay, all of the light is just contained in that laser beam and it's not radiating in any other direction. So that would not be an isotropic source because of course it's radiating only in a single direction and it's not spreading it out evenly in all directions. So again, a laser beam would not be isotropic, but something like a light bulb, that would be isotropic. Okay, so with that said, let's imagine we have a three-dimensional medium for our waves to move in that has no dissipation. So it means the wave energy is not being converted to internal energy. We don't have things like friction that take away wave energy. So no dissipation, okay? So if that's the case, the intensity of the waves that are emitted by an isotropic source are going to have to follow what we call an inverse square law. That means the intensity is proportional to the distance to the -2 power. So 1 over the distance squared, in other words. That's the inverse square law for you. So let's derive this, let's see where it comes from, and then we'll talk about how we can use this. Okay, so we'll start by drawing a little dot, and that represents the source of the waves. And to show that it's giving off energy evenly in all directions, we'll draw some arrows. So these are the rays, which indicate that we have waves traveling out in all directions. The next thing we'll do is draw a little sphere around the source. So this is a spherical surface with a radius of r. Okay. So if we want to talk about the intensity of the waves, intensity, remember, is the energy per unit time per area that's passing through the surface. Now, in this expression, I have energy divided by time, E over T, and I want to remind you that energy over time is just power. Power is the energy per unit time. In this case, to be a little bit more specific, what I'll call P surf would be the energy per unit time passing through the surface. Okay, and I'm talking about the spherical surface that we just drew. So, the intensity of the waves that are passing through the surface would be P surface divided by S. Okay? Now, what's S? S is the area of the surface. And since the surface is spherical, the area is 4 pi r squared, because that is the surface area of the sphere that surrounds the source. Okay, so next, just remember that there's no energy loss in the medium. Okay, so that means all the energy that's emitted by the source will have to go through the surface. Okay, in other words, this little dot at the center of our picture is the source, and then it carries energy away from it, which eventually goes through the surface that we drew. But of course, if we're assuming there's no dissipation, the medium itself doesn't eat up any of our energy, then anything that's emitted by the source is eventually going to have to go through the surface, which is to say that P surface, the energy per unit time that goes through the surface, is P source, the energy per unit time that's emitted by the source, okay? That's true as long as we have, again, no energy loss in the medium. So therefore, the intensity of the waves is P source divided by the area, which is 4 pi r squared. And that's where the inverse square law comes from, because we have intensity proportional to r to the minus 2. That's the inverse square law. Okay, so that's the result that we wanted to derive. I is equal to P divided by 4 pi r squared. I is the intensity of the waves. P is the power output of the source of the waves. And then r is the distance from the source. So the basic idea here is that intensity, again, falls off like the distance squared. That's the inverse square law. And we're making a whole bunch of assumptions when we use the inverse square law. Again, we're assuming the source is isotropic. We're assuming the waves are moving in 3 dimensions. And we're assuming that there's no dissipation. But as long as all of those things are true, the intensity will follow an inverse square law. And so let's try to understand the inverse square law in a more conceptual way. Because the basic idea is that the energy carried by the waves is not lost as it moves away from the source. The energy just becomes more spread out. And that's why the intensity goes down as you get further away from the source. So if we take a look at this picture here, where S represents the source of some waves, and we can take a look at some rays here that are shown in red, representing the direction the waves are moving in. And we're not going to look at all the different rays. We'll just look at some of them. Okay, just a little bundle of rays here. So if we start by looking at a distance that we'll call r away from the source, then those rays will be moving through a certain area, which we'll call A. And then if we imagine increasing the distance by a factor of 2, so now we're a distance of 2r away from the source, well, now those rays are moving through a bigger area. And in fact, the area is increased by a factor of 4. We can fit 4 of those original areas into this new larger area. And then if we increase the distance even more, so now we're a distance 3r away from the source, well, now the area that those rays are moving through is even bigger than before. Now it's actually 9 of those original areas that you can fit inside of this bigger area. So the point of all this is to say that the area that your waves have to pass through increases with the distance squared. So the area is proportional to the distance squared. But intensity is what we care about here. And remember, intensity is the energy per unit time per unit area. So in other words, the energy that's passing through these different areas is not changing at all, but the area is. And since when we deal with intensity, we're dividing the area out, area is in the denominator, the intensity must be decreasing with distance. And in fact, it's decreasing with distance squared, okay? So if the area is proportional to r squared, the intensity is proportional to r to the minus 2. And that's where the inverse square law comes from. Energy is not disappearing, it's not going away. It's just having to move through a bigger and bigger area as you move away from the source, which is why the intensity is decreasing. Okay, so let's do an example of this. We have Alice over here standing 13.5 meters away from an isotropic light source, so you can imagine something like a light bulb. Bob is standing 24.5 meters away from the same light source. So the question is, what is the ratio of the light intensities that Bob and Alice receive? So what's the ratio of intensity for Bob and intensity for Alice? The second question is, what is the ratio of the amplitudes of the light waves that Bob and Alice receive? So what's the ratio of amplitude for Bob and amplitude for Alice? So let's work this out. Okay, so we're going to start with the result that we derived just a second ago. Intensity is equal to power of the source divided by 4 pi r squared. Okay, let's rearrange that a little bit to say that I times r squared is equal to the power output of the source divided by 4 pi. And if we look at it this way, in particular, we focus on the right-hand side, the power is just some constant for the source, and 4 pi, of course, is just another constant. So overall, what we have is a constant quantity on the right-hand side. So that means I times r squared should be the same for Alice and Bob. So what we can then say is I, intensity of the light that Alice receives, times r squared, that's the distance for Alice, is equal to IB, that's the intensity of the light that Bob receives, times Bob's distance away from the source. So that would be RB squared. Okay, what we want here, if you recall, is the ratio of the intensities. So the intensity for Bob divided by the intensity for Alice. Well, that should just be RA divided by RB squared. Okay? And we could put a number to this because the distance for Alice, RA, is 13.5 meters, and RB, Bob's distance away from the source, is 24.5 meters. So we have 13.5 over 24.5 squared. And this works out to 0.3036, keep 3 sig figs, 0.304. That's the ratio. So Bob is only receiving about 30% of the intensity that Alice is receiving. Okay, next we want to talk about the amplitudes of the waves. So I'm going to remind you of a result that we derived earlier. Intensity of a wave is equal to 2 pi squared times rho times v times f squared times a squared. Let's just focus on the fact that in this expression, we can divide out a squared to write this as 2 pi squared rho times v times f squared. And all of this here is just a constant, right? It's referring to the frequency of the light, the density of the medium, and the speed at which we're moving through the medium. This is all one big constant. So in other words, intensity divided by amplitude squared is a constant, which means we can write the intensity that Alice receives divided by the amplitude of the waves that Alice is receiving squared is equal to the intensity that Bob receives divided by the amplitude of the waves that Bob receives. And what we're trying to get at here is the ratio of those amplitudes. So we have amplitude for Bob divided by amplitude for Alice squared is equal to intensity for Bob divided by intensity for Alice. So of course, we want to square root both sides of this thing, which will give us amplitude Bob over amplitude Alice equals the square root of the ratio of intensities, but that's something we calculated over here. So I have 0.3036, and the square root of that is 0.5509. Keep 3 sig figs, this is 0.551. So what that's telling us is the waves that Bob is receiving have about 55% of the amplitude of the waves that Alice is receiving. So Alice is receiving more intense light with higher amplitude. That's what's being shown here. Okay, so here's another example. The power output of the sun is 3.846 times 10 to the 26 watts. The Earth is on average 149.6 million kilometers away from the sun. What is the intensity of the sunlight that hits the Earth? And we're going to measure this in watts per square meter. Now, as a follow-up, the average distance between the planet Neptune and the sun is 4.496 billion kilometers. So in that case, what is the intensity of the sunlight hitting the planet Neptune? So pause the video, try to work this out, and of course, we're going to be using the inverse square law. So let's see what you get. Come back to the video after you work this out. Okay, so we'll start by thinking about the intensity of the sunlight hitting Earth. And we'll use the formula that we derived. Intensity is the power of the source divided by 4 pi r squared. Now in this case, the source of these light waves is the sun, and the power is 3.846 10 to the 26 power watts. So it's a very powerful source. On the bottom we have 4 pi, and then we put the distance between the Earth and the sun as r. So we have 149.6 million kilometers. So a million is 10 to the 6, and a kilometer is 10 to the 3 meters. So this is how we take the distance and express it in meters, 10 to the 6 times 10 to the 3, and then we better square that as well. Okay, so if you calculate this, you'll get 1,367.5. Units are watts per square meter. We'll round it to 4 sig figs, because the numbers we're plugging in have 4 sig figs. And this is 1,368 watts per square meter when we round it. Okay, there's a little bit of a complication here that I want to point out. You probably know that near the equator, temperatures are very high, and if you're near the North Pole or the South Pole, the temperatures are very low. So it's not like the intensity of sunlight is really the same everywhere on Earth. So let me just draw a picture for you. This is the surface of the Earth, and here are some rays of sunlight coming in. So the point is, if we're near the equator, the sunlight is hitting the Earth pretty much head on. In other words, the sunlight is moving perpendicular to Earth's surface. And remember, when we calculate intensity, we're always assuming that the light is moving perpendicular to the surface. So that's definitely the case near the equator. So the intensity would be exactly what we calculated. Now, on the other hand, if we're near the poles, so the North Pole up here, maybe the South Pole down here, the sunlight is not hitting the Earth head on. It's kind of hitting it at a glancing angle. So the sunlight is not moving perpendicular to Earth's surface, and therefore the intensity is actually less than what we calculated. So strictly speaking, this would be the intensity if you're right at the equator. As you start moving towards the poles, you'll get something less than that. Okay? So next, let's think about the intensity of the sunlight that reaches Neptune. Okay, so same formula as before. Intensity is P divided by 4 pi r squared. The power is the same. We're still talking about the sun, of course. 3.846, 10 to the 26 watts per square meter. And then we'll divide that by 4 pi, and then the distance, which is 4.496. Okay, we had 4.496 billion kilometers. So a billion is 10 to the 9. And again, a kilometer is 10 to the 3 meters. So to get that distance in meters, this is how we would do it. And then we'll square that. So we get only 1.5141, keep 4 sig figs, watts per square meter. And so that would be 1.514 watts per square meter. So the intensity that's hitting Neptune is much, much less than the intensity of the sunlight that hits Earth, which is why Neptune is such a cold and dark planet compared to Earth. Okay, so here's another question for you to think about. In a two-dimensional medium with no dissipation, how would the intensity of waves emitted by an isotropic source fall off with distance? Okay, so we know in a three-dimensional medium that the answer is they follow the inverse square law, so I would be going like r to the minus 2. But try to work out what this would be for a two-dimensional medium, okay? And then as a follow-up to that, what would the answer be if you had a one-dimensional medium, okay? So pause the video, think about this for a second, and see if you can come up with your answers. Okay, so there are two parts to this. Let's start with intensity in a 2D medium. So if you want to picture something concrete, think about the waves on the surface of water in a pond. So if you drop a rock into the water in a pond, little ripples spread out in 2 dimensions, okay? So to show the source of the waves, I'm going to put a little dot here. And we'll show that the waves are spreading out evenly in all directions using these rays here. But if you were to ask, what kind of shape is it that these waves are moving through? Well, you can draw it, and it's a circle. Okay, so the energy of these waves is passing through a circle. And the circumference is 2 pi r. So we're not dealing with a sphere anymore, as we would be in 3 dimensions. All of these waves are just passing through that circle. So the intensity would be the power output of our source. But again, since the waves are moving through the circumference of a circle, we would have to divide by that. And so we have the power output of our source divided by 2 pi r, and we don't really care about these constants out front. We just want to show that the intensity does not follow an inverse square law. It's r to the minus 1 in a 2-dimensional medium. Okay, what about in a 1-dimensional medium? So the intensity in a 1D medium, how do we kind of show that we have a source of waves? Well, I'll just put a little dot here. I'll draw a little dashed line to represent our 1-dimensional medium. So a wave could be moving to the right, or a wave could be moving to the left. But that's really it. That's how we show a source of waves in a 1-dimensional medium. So then, if I think about, some other point, let's call this point P, right? The energy passing through that point does not depend on the distance from the source. Okay? Because of course, if I picked a different point, let's say over here, let's call this one P1 and this one P2, the same exact amount of energy would be passing through each one of those points because the energy can't spread out when it's in one dimension. It can just move along the line. If you're in two dimensions, you can see that the energy spreads out as you get further away from the source, and that's also true in three dimensions. But in one dimension, that energy just can't spread out. Energy doesn't spread out in 1D. So for that reason, the intensity is just constant. It doesn't fall off as you get further and further away from the source if you're in one dimension, okay? So those are the answers to these two questions. And that's where we'll end this video. So I'll see you in the next one. In the next video, we're gonna wrap up this chapter and finish this lecture on chapter 15. So until then, as always, be safe out there, be healthy. I'll see you in the next one.